There's a measurement engineers use when they want to express the size of a jet engine fan. Not diameter in inches, not weight in tons. They ask whether a person can stand inside one of the blades. For the GE9X, the answer is yes. That detail sounds like a party trick, but it's actually the most honest summary of what GE set out to build, and why it cost the aviation industry so much time, money, and quiet anxiety to get there. The story of the GE9X doesn't begin with a decision to build the world's most powerful commercial jet engine. It begins with an airline problem. The Boeing 777X was conceived as the next evolution of the world's most successful twin-engine widebody. Longer range, higher capacity, better economics than anything currently flying long-haul routes. For airlines like Emirates, Lufthansa, and Qatar Airways, operators running ultra-long-haul routes where fuel burn is everything, it represented a genuine generational leap. But a more capable aircraft needs a more capable engine. And the GE90, legendary as it was, had limits. Scaling it incrementally wasn't going to deliver what the 777X promised. So GE Aviation made a decision that engineering programs rarely make. They didn't refine. They rebuilt almost from the ground up. The GE9X would carry a 134-inch fan diameter. That's the largest ever fitted to a commercial engine. A bypass ratio pushed to extremes not previously attempted in a certified production program. An overall pressure ratio that, on a spec sheet, looks like a number someone invented to win an argument. On paper, all of this translates to something airlines care about deeply: fuel efficiency. Over a 20-year fleet life cycle, the projected savings run into the hundreds of millions of dollars per operator. But here's the thing about engineering at this scale. The spec sheet is optimistic by nature. Reality is not. When you increase an engine's fan diameter, you don't simply get proportionally more airflow. You enter a different engineering regime entirely. Weight compounds faster than performance. Airflow becomes harder to manage. Small tolerances that were acceptable at lower scales become meaningful sources of instability. And vibration. At this size, with a rotating assembly spinning thousands of times per minute, vibration isn't a comfort problem. It's a structural integrity problem. Aviation has always advanced through incremental steps. That's not timidity. It's the rational response to an environment where failure has consequences beyond budget overruns. Engines are certified components. They carry people. They operate in conditions that ground-based testing can only approximate. GE Aviation understood all of this, and they built the GE9X anyway, because the other option was ceding the most important commercial aircraft program of the coming decade to a competitor willing to take the risk. In aerospace, sometimes the most dangerous choice is the cautious one. Inside any jet engine, a war is happening. It's the war between heat and material, between the temperature required for maximum efficiency and the temperature at which the metal surrounding that combustion simply stops holding together. The combustion core of the GE9X operates above 2,500 degrees Fahrenheit. That's hotter than the melting point of most conventional turbine alloys, which raises an obvious question. What are the blades made of? The answer is ceramic matrix composites, CMC. Materials engineered not to conduct heat the way metals do, allowing them to survive temperatures that would reduce a conventional alloy component to slag. Lighter than the metals they replace. More thermally resistant. A genuine materials science breakthrough, not theoretical but deployed at scale inside a flying engine. GE had been developing CMC technology for years before the GE9X program. But applying it inside a production engine at this operating scale in this thermal environment was different from laboratory certification. Alongside the ceramic components, GE deployed two other manufacturing technologies that had never previously been combined at this scale in a commercial program.
3D printing.
Not as a prototyping tool, as an actual manufacturing method for certified flight hardware. The fuel nozzles of the GE9X are printed components. Not assembled from hundreds of machine parts, but grown. That's the accurate word, layer by layer in a precision additive manufacturing process. What previously required 855 separate parts now requires 20. Fewer joints. Fewer potential failure points. Complex internal geometries that conventional machining cannot produce. And then there's the cooling architecture. Jet turbine blades have been internally cooled since the 1960s. Compressed air routed through channels inside the blade creates a thermal barrier between the metal and the heat trying to destroy it. The GE9X took this to its logical extreme: microscopic channels, some narrower than a human hair, carrying cooling air to precisely where the thermal load is highest. 3 breakthrough technologies working in concert, each independently impressive, together genuinely transformative, and also genuinely untested at operational scale. This is the tension at the heart of the GE9X development story. Every innovation that made the engine more capable also made it harder to certify, because certification at its core relies on precedent. The FAA asks a straightforward question: how do we know this component will perform safely over tens of thousands of flight cycles? For conventional alloys, there are decades of data, known failure modes, predictable wear patterns, a library of real-world performance history. For ceramic matrix composites in a production turbine environment, for additively manufactured fuel nozzles operating at extreme pressure, the data simply didn't exist yet. GE was going to have to generate it. That process is called a type certification campaign, and it is, by any reasonable measure, one of the most demanding intellectual and industrial endeavors in civilian manufacturing. Thousands of hours of ground testing, bird ingestion tests, ice crystal tests, crosswind tests, blade-off containment tests where a fan blade is deliberately shattered at full speed to verify the engine casing holds, and endurance cycles, extended simulations of a full operational lifetime, compressed into months of continuous testing. It was during endurance testing that the program hit its defining moment. There's a particular kind of silence in an engineering program when test data doesn't match the model. Not the silence of catastrophe, the silence of uncertainty. The moment when the question shifts from, will this work, to, do we understand why it's not working the way we said it would? Deep into GE9X endurance testing, the ceramic matrix composite components showed where, not catastrophic failure, not sudden fracture, gradual degradation, but at a rate and in a pattern that the simulation models hadn't predicted. This is arguably the most dangerous kind of engineering problem, because a dramatic failure is paradoxically easier to understand and address. You can see what broke. You can identify the failure mode. Unexpected degradation, where that differs from prediction in both rate and geometry, means something in your fundamental understanding of the material behavior is incomplete. And the FAA will not certify a component whose behavior its own designers can't fully predict. What followed was not a single dramatic redesign. It was something more exhausting, an iterative campaign of adjustment and retesting that consumed months. Blade geometries were revised. Cooling channel configurations were refined. Thermal modeling was recalibrated against actual test data. Then the tests ran again and again. This is the part of aerospace development that doesn't make press releases. There's no announcement for, we discovered our material model was incomplete and have been running iterative corrections for the past 14 months. But this is where aircraft programs actually happen. In the gap between the performance promised on a launch slide and the performance demonstrated in a certification data package. Meanwhile, Boeing was watching. The 777X program had been structured around a delivery timeline. Airlines had placed launch orders. Fleet planners had built retirement schedules around expected delivery windows. Route networks had been designed around the 777X's range capabilities. When engine certification slips, nothing else can move forward. You cannot fly a 777X on a different engine. The GE9X is not interchangeable with anything else in production. The aircraft was designed around it, structurally, aerodynamically, electrically. Engine delay became fleet delay. Fleet delay became airline planning disruption. Airline planning disruption became financial pressure on Boeing. a manufacturer already navigating one of the most difficult periods in its history. The GE9X delay didn't exist in isolation. Compounded. That's how program risk works in aerospace. A material science problem inside a test cell in Ohio becomes a capacity planning problem for an airline in Dubai. The connection is direct, and the distance between them in time, in money, in consequence is vast. Let's be precise about what the GE9X actually achieved. It works. It's certified. It powers an aircraft that, by every performance metric, represents the peak of large widebody capability. The fuel efficiency numbers are real. Compared to the engines the 777X replaces in long-haul service, the GE9X delivers meaningful fuel burn improvements that, over a typical fleet lifecycle, translate to genuine competitive advantage for the airlines operating it. When you fly London to Sydney or Los Angeles to Dubai, fuel cost is not an abstraction. It's the largest single operating expense on the route. An engine that burns less, not marginally but significantly, changes the economics of that operation. The engineering achievement is not in question. But look at what it cost. A development program spanning more than a decade. A certification campaign that required fundamental revisions to new generation materials. Delay timelines that rippled through one of aviation's most commercially important aircraft programs. Engineering complexity so unprecedented that the manufacturer spent years simply building the knowledge base to understand what they'd built. The GE9X didn't just push commercial aviation forward. It revealed exactly where the ceiling of a particular engineering philosophy sits. The philosophy of scaling up. More bypass, more pressure, bigger fan, better materials to survive what bigger fan and more pressure produce. The GE9X is the fullest expression of that philosophy in commercial aviation history, and the program demonstrated conclusively that you can get there. But also, more quietly, that the path gets harder every step. Not everyone looked at the GE9X and decided to push further in the same direction. Rolls-Royce's next-generation propulsion program, UltraFan, is built on a fundamentally different premise. Rather than maximizing bypass ratio through a larger fan directly driven from the turbine shaft, UltraFan introduces a gearbox between the two. Power gearbox, allowing the fan to spin at a different, optimal speed from the turbine, decoupling two systems that have historically been locked together. The engineering logic is compelling. When the turbine drives the fan directly, you're always making a compromise. The fan wants one rotational speed, the turbine wants another. The gearbox eliminates that compromise. It also adds mechanical complexity. A power gearbox capable of handling the loads involved, in an environment of vibration, thermal cycling, and decades of continuous operation, is not a trivial engineering challenge. Pratt & Whitney reached a similar conclusion with their PW1000G geared turbofan, now in service on Airbus A320 family aircraft. The concept works. The implementation has had its own development challenges. But the direction is clear. Two different engineering philosophies, pursued by two of the most sophisticated propulsion organizations on the planet. GE's approach: maximize every parameter within a direct drive architecture, use advanced materials to survive the consequences. Rolls-Royce's approach: change the fundamental mechanical relationship between the turbine and the fan, accept the gearbox complexity, gain rotational freedom. Both have merit, both carry risk, and both will shape the aircraft that enter service in the 2030s and 2040s. The competition here isn't simply about who builds the better engine. It's about which engineering philosophy proves more durable over the next generation of commercial aviation. More sustainable, more certifiable, more capable of the step-change efficiency improvements that the industry needs as it navigates carbon commitments, fuel price volatility, and the growing pressure to find alternatives to conventional kerosene. There's a tendency when covering programs like the GE9X to frame the story around the delays. The delays were real. Their commercial consequences were significant. Nobody who had placed launch orders for the 777X and restructured their fleet planning around it would describe the experience as inconsequential. But focusing on the delays misses the more important story. Commercial jet engine development has always been, at its core, a process of discovering the limits of materials and manufacturing. The Rolls-Royce RB211, which launched the high-bypass turbofan era, nearly bankrupted the company when its carbon fiber fan blades failed bird ingestion testing. Rolls-Royce nationalized. The program survived. The technology redefined commercial aviation for 50 years. Pratt & Whitney's JT9D, the engine that made the 747 possible, had blade failures in early service that resulted in significant operational restrictions and program scrutiny. The problems were solved. The 747 flew for half a century. The pattern is not new. It's the pattern of engineering at the frontier. What changes is the cost. In 1970, a turbofan development program cost hundreds of millions of dollars. Today, a program at the scale and ambition of the GE9X costs multiple billions. The number of organizations globally capable of financing, designing, and certifying an engine at this level has not grown. In some ways, it has shrunk, which raises a question worth sitting with. If the barriers to entry in commercial jet engine development continue to rise, if the capital requirements, the certification complexity, the manufacturing precision required keep increasing, what does the competitive landscape of aerospace propulsion look like in 2045? China's COMAC is developing the C919 narrowbody with CFM LEAP engines, Western propulsion on a Chinese airframe. Their longer-term ambition includes domestic engine development, but the gap between ambition and certification-ready hardware is measured in decades, not years. Russia's civilian aviation sector has been dramatically set back by sanctions and supply chain isolation following the invasion of Ukraine. The field of credible commercial turbofan manufacturers remains essentially what it was 20 years ago. GE, CFM, Pratt & Whitney, and Rolls-Royce. The GE9X's development cost didn't just produce an engine. It reinforced the barriers. It demonstrated that producing hardware at this performance level requires industrial resources and institutional knowledge that can't be acquired quickly. That's not incidental to the GE9X story. It is the GE9X story. A technology program this ambitious, this expensive, this difficult, is simultaneously a product development effort and a geopolitical statement. About who can build what. About which industrial bases possess the knowledge and capital to remain relevant at the frontier of aerospace. The GE9X is flying now. The Boeing 777X has completed its certification campaign. The engine that was, for several years, the central uncertainty in one of aviation's most consequential programs is now routine flight hardware. It's tempting to read that as vindication, to say that the delays were the price of ambition, and ambition was worth paying for. That's partially true. But what the GE9X actually demonstrated more clearly than any single engineering achievement is that the direct drive turbofan architecture, scaled to its logical extreme, has reached a ceiling. Not a hard stop, a ceiling. A point where incremental performance gains require disproportionate development investment. Where each additional percentage of efficiency improvement demands a step change in materials science, manufacturing technology, and certification rigor. The engineers who built this engine know this. The engineers at Rolls-Royce who are pursuing a geared architecture know this. The industry planners who have to model next-generation programs against sustainability targets know this. The next great leap in commercial propulsion efficiency probably won't look like a bigger GE9X. It might look like a geared turbofan at a scale that hasn't yet been attempted. It might be a hybrid electric propulsion system that borrows from automotive and aerospace simultaneously. It might be an open rotor, an unducted fan architecture that trades aerodynamic elegance for efficiency gains that duct engines simply cannot achieve. It might be something that hasn't yet cleared the conceptual phase. What it won't be is a refinement of the same philosophy that produced the GE9X. The GE9X made sure of that. Not by failing, but by succeeding so thoroughly that the path forward now runs in a different direction. That's an unusual legacy for an engineering program. Not a dead end. Not a failure. A genuine achievement that, by achieving everything it set out to achieve, made its own approach obsolete. Aviation moves forward by finding out where the ceiling is, then building something new below it. The GE9X found the ceiling. The next generation is already being designed.